Okay, so we just finished talking about these words, the experiment, the sample space, and we also used the word event, but we haven't really clearly defined that yet. So let's just define that in terms of these others. So let's take the experiment was, all right, the experiment was toss two coins, that we did that one, and the sample space, I'll call it capital S, just the standard way. Sample space, we said was HH, HT, TH, and TT. We said that. And then we can talk about the events. Let's talk about, well, there are different events. For example, we could talk about the event of getting two heads, or we could talk about the event of getting two tails when we toss two coins, or we could talk about the event of getting one tail, and so on. We could talk about lots of different events. So let's just bring up one event. Let's say the event of getting one head, exactly one head. So remember, we had other events in other experiments. For example, the event that it would rain, or the event of getting an even number when we tossed a die, when we rolled a die. The event of getting an even number. Here, I'm talking about the event of exactly one head. So what is that event? We say that this event, let's call it H, for example. Well, maybe not H. Let's call it E. So E would be HT and TH. Okay, so that's the way we would express this event of getting exactly one head, because these are the set of possible values that we could get, or possible outcomes that we could get, and two of them result in getting exactly one head, right? So these two give us exactly this event. Okay? Let's just do one more example. Let's suppose we went back to the experiment. Instead of tossing two coins, the experiment of rolling a die. So let's say roll a die, and then the sample space would be 1, 2, this is what we said before, 3, 4, 5, and 6. And then we can also talk about some event there as well. For example, the event of getting, I think we said the event of getting an even number, let's call that E. And so we're the event of getting an even number. So again, we're going to sort of do it the same way. That is, we're going to write out which of these will give us that would result in such an event. So we're going to say 2, 4, and 6. Any of those would give me an even number, just like either of these would give me exactly one head. So we want to list all of the elements in the sample space which would result in something like this, which would result in exactly one head, or which would result in getting an even number. So that all of the elements in the sample space that would give me an even number, that's 2, 4, and 6. So these two examples are two examples of what we call events. So let's kind of think about how can we talk about events? And if you think about it, this E here, the green E here, is a subset of this sample space, right? This is a subset of this sample space. And if you think about this E here, this orange E here, this is also a subset of that sample space. Now we could have another event. Suppose we talked about the event of getting a number more than 3. So the event of getting a number more than 3, that sounds like a reasonable English expression, the event of getting a number more than 3. So let's call that event F. So using this same kind of way of explaining the event, or writing out the event, what is that event? The event of getting a number greater than 3. So we just go through and say which of these would result in such an event. So which of these would result in getting a number greater than 3? Well, this wouldn't, this wouldn't, this wouldn't, but this would, 4, 5, and 6. So that's how we would express the event of getting a number greater than 3. So how are we expressing events? How did we express the event here, the green one, of getting exactly 1 head? How did we express the event of getting an even number? How did we express the event of getting a number greater than 3? How are we expressing events? We're expressing them as what we say are subsets of the relevant sample space, or the pertinent sample space. So these two are both subsets of this sample space, and this one is a subset of this sample space. So that's what we're just going to use that idea to say that's what we mean by events in general. So an event is any subset of the sample space. And the sample space we usually denote by an S, so I'll write that. Any subset of the sample space. So that is that's how we're going to define this word event. Okay, now let's go back to thinking about experiments again, and how to get the sample spaces, or the sample space. And here, I wrote it out like this, but if I had changed this to 3 coins, then, thinking about what the sample space should be is a little bit hard to do. So we can use a tree diagram. And what I mean by that is, so we could say, a tree diagram, usually you just have a starting point here. And then we talk about the what would happen for the first die. And we know that we could get a head or a tail. And then given that we got, so I'm trying to get all of the outcomes for tossing 3 coins. When I tossed 2, I had this list here, but I want to get for 3 coins. So I'm going to use this kind of structured way to get it. So, okay, so the first die could be heads or tails. Now, given that I got heads on the first die, I could still get heads or tails on the second die. So I'll use this tree and write it like this: H and T, and H and T. And so if we just stopped with this, we would say, okay, the outcomes that we can get when we toss 2 dice are HH, HT, TH, and TT. In other words, these 4 here. But let's do it now for 3 dice. 3 tosses, 3 coins. So here's the 3rd coin. So now I can get H here and tails here, or H and T here, and H and T here, and H and T here. So now I can read to get all of the outcomes. I can say the first outcome I could get when I toss 3 coins is H, H, H. So I could write that down, H, 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 H. And then I could write down this one, H, H, T. and so on. And I'd get all of them. And you can see the ones that I'm going to get. There's going to be 1, 2, 3, 4. So that's 4. And then there's just going to be a mirror. This is like a mirror of that. So there's going to be another 4. So altogether, there are going to be 8 outcomes. The last one is going to be T, T, T. Okay, so we can use tree diagrams to arrive at this kind of, to enumerate the sample space for a kind of more complicated experiment. Okay, next thing we want to do. So in the book and in many books, they talk about something called counting, but we're not going to have time to do that here. But you know, the question might be if you have something like, so this was a kind of counting problem actually. How many different outcomes are possible? And we said there were 8. But other kinds of counting problems are like, suppose you have this list of items, A, B, C, D, E. So 5 items. And how many ways can you select 3 from these 5? So we could select A, B, C. That would be one way. Could select A, B, D. That would be another way. So the question is, how many are there? So we're not going to go into this, but that's called counting. And we use symbols like this, C, N, R, and we use symbols like this, P, N, R. But anyway, we don't have time to do that here, so we're not going to do that. So let's go now and talk now about the word probability, which is we do want to talk about. We definitely want to talk about that. That's what the whole chapter is about. So let's talk about this word probability. So first of all, we said that probability is always going to be between 0 and 1. So it's never going to be less than 0. We don't say the probability that it will rain tomorrow is minus 20%. And we don't say the probability that it will rain tomorrow is 120%. So it's always between 0 and 1. So let's just write that. That is, for anything that we talk about the probability of, or any event that we talk about the probability of, it always has to be between 0 and 1. So when we talk about the probability that it will rain, or the probability of an even number, those are events that it will rain, that you get an even number, that you get what was here? This was this one. What was this? This was of getting exactly 1 head. So whatever you're talking about the probability of, you always call that the event. So the event would be of getting exactly 1 head. And then you write it, we will write it, as we would put the event. So this might be of getting exactly 1 head. And we want to know the probability of that. The way we ask that question is we say, what's this? That's just a notation to say, what's the probability of that event? So if the event was getting exactly 1 head, this would be, what's the probability of getting exactly 1 head? And all we want to say right here is that it's never going to be less than 0, and it's never going to be more than 1. So we can write that like this. It's never going to be more than 1. And we can write the other one, it's always going to be greater than or equal to 0. So that's the first thing we want to say, that whatever event we're talking about, no matter what it is, it's never going to have a probability of less than 0, and never going to have a probability of more than 1. Okay, the next thing we want to say, and we can also say, now, we said that an event is any subset of the sample space. So this here, what I have in green here, that's a subset of the sample space. We called it, I think we called it E. I called it green E, but I called it E, and it looked like this. That is a subset of the sample space. every event is a subset of the sample space. So, and we also called each one of these things, if you remember, I asked everybody to repeat it. We called each one of those things a sample point. Each one of those is a sample point. So this event E consisted of two sample points, HT and TH. This whole sample space consists of 4 sample points. So usually most books, they'll denote the sample points, at least in our book, I think they are, like this, E sub I. Maybe, I don't know. But let's try and use that right now. So let's say this is, by E sub I mean one of the sample points. So this might be E sub 1, this might be E sub 2, this might be E sub 3, this might be E sub 4. And then this consists of 2 of those sample points. So not only can we say this, but we can say specifically for any of the sample points also. Of course, this has to be true because this has to be true for every event. Oh, sorry. The sample points themselves are events, right? Because they are, if I just say, okay, E1, let's say E1 is HH, that's also an event. That's, first of all, in words, that's the event of getting exactly 2 heads. And also, we can say it's an event because it's a subset of the sample space. So it's an event. So these are specific events. These are like the simplest possible events because they only consist of 1 element in them. You know, this was a little more complicated, this event of getting exactly 1 head, that had 2 elements in it. But these sample points are also events because they are also subsets of the sample space, but they're really simple ones, right? So anyway, this was true for any event. So of course, it's also true for this. We can also write this. Okay, so we can also say that. Now, the next thing we want to say is that, well, let's go back. Let's go to this example. S equals 1, 2, 3, 4, 5, 6. Now, can you read that? I think you can read it. I hope. 1, 2, 3, 4, 5, 6. So, well, of course, what am I talking about there? What experiment am I thinking about? I'm thinking about rolling a die, right? Rolling a die. Let's see, we have a green die. Okay, so we have a green die. So this is the sample space for that, for rolling a die. Now, if I ask anybody, you know, what's the probability of getting a 5? What's the probability of getting a 5? See if you can see this here. Getting a 5, everybody, most people are going to say the probability of getting a 5 is 1/6. If I ask everybody, what's the probability of getting a 1? Same thing, everybody's going to say the probability is 1/6. If I ask everybody, what's the probability of getting a 2? They're going to say the probability is 1/6. So the probability of each of these elements in the sample space, we think of them as all the same, and we say they're equally likely, and in this case, since they're equally likely, and there are 6 of them, we think of the probability of any particular one as 1/6. So we might write the probability of getting, we're going to put it in brackets whenever we talk about an event, at least I'm going to. So let's say the probability of getting a 2. I'm going to put that in brackets to indicate that it's a subset of the sample space. So maybe you think that's too much. but I like to write it in brackets because I want to remember that every event, including this one of getting a 2, is a subset of the original sample space S. So I put it in brackets. So anyway, the probability of that is 1/6. And also the probability of, like, what did we say, a 5, I'm going to still put it in brackets so that I remember that it's a subset of the sample space, and that's also 1/6. So they're all 1/6. And so if we add them all up, now remember, what do we mean by E sub I? We mean these individual events. They're called simple events, actually. Usually they're called simple events. So this one is not a simple event, but if I just wrote, let's say I just wrote this one, let's see here, E1, if I just wrote that, so I only had one element, this is just one element, that would be called a simple event. So we use the word simple event. So anyway, these are all, this is a simple event, this is a simple event. And in this case, the probability of all the simple events, they're each 1/6. And furthermore, if we add up all of the probabilities of all the simple events, well, let's write that out using white chalk. So if I take the probability of E1 plus the probability of E2, and I go all the way up to the last one, which is, in this case, there are 6 of them, 1, 2, 3, 4, 5, so E6. Hope you can read that. Then I get 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, whatever, 1/6. That's going to equal 1. And if I did the same thing here, now here I only have E1, E2, E3, E4. There's only 4 simple events. So we would tend to think that the probability of this one is 1/4, 1/4, 1/4, 1/4. And again, if you add those all up, you also get 1. So what we're saying is that when you add up the probabilities of all the simple events, you get 1. No matter how many simple events there are. In this case, there are 6 simple events. But if you add them all their probabilities up, you get 1. Same thing here. There are only 4 simple events, but if you add up all of their probabilities, which is 1/4 plus 1/4 plus 1/4 plus 1/4, you also get 1. So we just say, in general, if we sum up the probabilities of all the simple events, we expect to get 1. I guess we could write that like this. We could say sigma means to sum them all up of all the simple events. So that would mean E1 plus E2 up to E6 here, or it would mean E1 plus E2 plus E3 plus E4 here. But if you sum them all up, you should get 1. So now we have another statement that we can make. So we have like 2 statements we've made so far. So here's one. This was one statement, and this is another statement. We have these 2 statements. First statement says that the probability of any event is between 0 and 1, and this is sort of the same, another version of that, but actually this one is more general. This is specifically only for simple events. They are also always between 0 and 1, but this just says for every event, it's always, the probability is always going to be between 0 and 1. And now we have something else interesting, which is that if we sum up the probabilities of all the simple events, we should get 1. Okay, so we just talked about sample spaces and experiments and events and probabilities. And we talked about one probability calculation, which was this one. So we thought, what's the probability of getting a 2? And that was in the context of rolling a die, and the sample space was like this. And we said that the answer was 1/6. But we want to think about how we can assign probabilities in general. So in this case, we think we knew the answer, and it seems pretty simple. But we want to think about how, in general, what do we do when we assign a probability, and then how do we actually do it? And it's typically broken down into three kind of ways of thinking about it. So there's what's called the classical method, which is what we actually did here. And then there's something called the relative frequency method. And then there's something called the subjective method. So let's take a look at these and see what they mean by this. So like we said, the classical method is basically what we just used. And here's the example actually that we just talked about. And that was when we're rolling a die. And so the classical method says something like this. If an experiment has n possible outcomes, so when we roll a die, of course, n is 6, right? We have 6 possible outcomes when we roll a die. If we toss one coin, then n would be 2 because we have 2 possible outcomes, heads and tails. So if an experiment has n possible outcomes, the classical method would assign a probability of 1 over n to each outcome. So that's what we did. We said, what's the probability of getting a 2, an outcome of 2 when we roll a die? And we said it's 1/6, and that's because there are 6 possible outcomes. So n is equal to 6, and we got 1/6. So that was for the experiment of rolling a die. This was the sample space, and each sample point has a 1/6 chance of occurring. So this is called the classical method. So what else can we do besides the classical method? So sometimes, let's suppose we have a die, but let's assume that the die is not very well made. Like suppose, I made it. I went out and I cut down a little piece of a tree, and I had a little knife, and I started to try and make a cube, and I had and then I put dots on the cube. But obviously, I'm not going to be able to make a very good representation of a perfect cube. So it's not going to be a perfect die. And so the probabilities are not really going to be equally likely. So the probability of a 1 is not necessarily going to equal the probability of a 5. It's not necessarily going to equal the probability of a 2, and so on. So we can't really assume that they're all equally likely. So how then do we assign probabilities to the different possibilities? So, we still have the same set of possibilities, 1, 2, up to 6, but they're not all equally likely now. So the only way really to do it is to just roll the die, keep rolling it. Roll it 10 times, roll it 100 times, roll it 1,000 times, roll it 10,000 times, and just count up the percentage of times I get a 1, the percentage of times I get a 2, percentage of times I get a 3, a 4, a 5, and a 6. So maybe, the percentage of times I get a 1 is 15%. And maybe the percentage of times I get a 2 is 10%. And the percentage of times I get a 3 is something else, maybe 12%, and so on. Now, one thing is that all these percentages have to add up to 1, otherwise it doesn't make sense. But other than that, they don't have to be equal. But I can then say, okay, for my die, the probability of getting a 1 is about 15%. The probability of getting a 2 is about 10%. The probability of getting a 3 is about 12%, and so on. So that would be another way to assign the probabilities. And this is called the relative frequency method, because what we're doing is let's look at it. Let's look at this example. It's not a die, but another example where we wouldn't know how to assign the probabilities. So if we use the classical method, we know how to assign the probabilities of 1, of 2, of 3, and so on. They're all 1/6, but if it's just a die that I made, it's not true anymore. And there are many, many cases, most cases, where we don't know how to assign the probabilities. So let's take a look at this thing, Lucas Tool Rental. Lucas Tool Rental, we'd like to assign probabilities to the number of car polishers. So I guess they make these, or they rent out these things that are used to polish cars each day. So the office records show the following frequencies of daily rentals for the last 40 days. Now let's look at this. So sometimes they didn't rent out any. Sometimes, so there were, in this data set of 40 days, there were 4 days when they never rented out any. And then some days they rented out 1 during that whole day. And out of these 40 days that they conducted the study on, there were 6 days that they rented out 1 polisher. And then some days they rented out 2. And in their study of the 40 days, there were 18 days when they rented out 2. And sometimes they rented out 3, and there were 10 days like that. And there were sometimes they rented out 4, and there were 2 days like that. And presumably they never rented out more than 4. So the number of days are here. And then we can, to get the probability, for example, that they're going to rent out 2, to get the probability that they might rent out 2 on a day, they'll take the 18, because there were 18 days out of the 40. So they'll take 18 divided by 40, and I guess that gives you this number. So we can think about this as being the probability that they might rent out 2. And we can think about this one. This is 10 out of 40, which is 25%. So we can think of that as the probability that they might rent out 3. Because there were 10 days out of 40 when they rented out 3. 10 days out of 40 is 25% of the days. So we can then use these as the probabilities. Now, otherwise, we'd have no idea, what's the probability that they're going to rent 1? What's the probability that they're going to rent 2? Who knows? We have no idea. It's not even, at least in this die, we say it could be maybe approximately 1/6. But here we have no clue as to what this should be. So that's when we would use this relative frequency approach. Now, why is it called relative frequency? This is called the frequency of the number of days that they rented out 0 polishers. This is called the frequency, the number of days that they rented out 2. So these numbers are called the frequencies. And then when we take them relative to the total number of days in the study, so we get 4 out of 40, that's called the relative frequency, because it's the frequency divided by the total number. That's called the relative frequency. So this, sometimes they call it F for frequency, and then this is F over N, where N, I think that's a different N than we saw before. It's not the same N. This is N, is the number of times we performed this. So we performed, it means in this case, we did 4 days, and we did 6 days. So we performed this 40 times, or anyway, the total number of days was 40. So that would be N here. So we get these numbers, and of course we said that all of these, just like I said up here, these should add up to 1. These should also add up to 1, and I guess they do. Okay, so that we've talked about what we called the classical method. So that was like when we said we'll assign equal probabilities to all the outcomes. So that gives us 1/6 for these. We said sometimes that doesn't make any sense. Like if I had a die that I made myself, it doesn't work anymore. And then we can revert to or use the relative frequency method, which means actually rolling the die many times, maybe 10,000 times, or checking some sample of sales or rentals, and looking at some sample, maybe a sample of size 40, and then calculating these relative frequencies, just like I calculated these relative frequencies. So those are two different methods for assigning probabilities to the different possible outcomes here. So the outcome could be 0. Polishers could be 1, could be 2, could be 3, could be 4. Here the outcomes could be getting a 1 on the die, a 2 on the die, a 3 on the die, and so on. And we assign probabilities to each of these outcomes. We assign probabilities to each of these outcomes. Okay? Now the last way that we talk about is what's called the subjective method. And that's like when you hear someone say, what's the probability that there's life on the moon? Well, we can't repeat anything, many times to do, like the last example, it was based on rolling the die many times, or repeating this number of days. Repeating the day many times. Basically, we sort of repeated the day 40 times, so we took 40 different days. We can't take 40 different examples of Mars, right? So we can't do anything like that. We can't say, well, here's 10,000 Mars planets, and 5% of them have life. So therefore, we can say there's a 5% chance that there's life on Mars, on our particular Mars. We don't have 10,000 examples of Mars. So we can't do anything like that when we're talking about something like the probability that there's life on Mars. But still, you hear scientists say things like there's some probability, they might give a number, for the life on Mars. So when they're doing that, when you can't repeat the experiment many times, like here, then we call this the subjective method. So when economic conditions or a company's circumstances change rapidly, it might be inappropriate to assign probabilities based solely on historical data. So there's another thing. We might have the rental data, but suppose suddenly there's a big change, big economic change, then it might not be such a good idea to use those past numbers, those past 40 days. It might not be a good idea to use this data to talk about what's going to happen, what's the probability that we're going to have 0 or 1, or be able to rent 2 or 3 or 4 of these. If suddenly things change, like suddenly there's a big virus that, and people can't go to work or something like that, then these numbers aren't going to really work anymore. So they say when economic conditions or a company's circumstances change rapidly, it might be inappropriate to assign probabilities based solely on historical data. We can use any data available as well as our experience and intuition. So we're talking about using a subjective method. So it means our experience and our intuition. But ultimately, a probability value should express our degree of belief that the experimental outcome will occur. So when we say there's a 5% chance that there's life on Mars, we're sort of expressing a degree of our belief that there's life on Mars. Or if we're doing this, going back to this, but suddenly there's a coronavirus, we can't really use this anymore, but we can still make guesses about what the probabilities are going to be. Now, maybe those guesses are going to be terrible, but we can still talk about doing that. And people will do it, right? You'll still do it, right? You'll say, okay, well, there's coronavirus now, but how many do you really think you're going to rent out this week? Or how many do you think you're going to rent out tomorrow? People will certainly do that. Whether it's going to be accurate or not is a different thing. Okay? The best probability estimates are often obtained by combining the estimates from classical or relative frequency approaches, which those are the two that we just discussed, with the subjective estimate. So we might say, oh, let's use our past data. So we'll use the relative frequency approach, but we're going to modify it because things have changed so much. Okay, so let's take an example. Let's look at that. So Bradley Investments, some kind of investment company, an analyst made the following probability estimates. So 10 to 8, 10 to minus 2, 5 to 8, 5 to, I'm not sure what this means, but net gain or loss. So let's say there might be an $18,000 gain in this investment, in some investment. I'm not sure what these are. There might be an $8,000 gain. There might be a $13,000 gain. There might be a $3,000, an $8,000, a $2,000. I actually don't know what these mean here. So I'm not sure why this is such a weird order, right? That you would think you would order it as 2,000 first, then 3,000, then whatever, 8,000 next, and so on. They have this weird order, and I don't know where this comes from. But anyway, let's just say these are different. This investment counselor our analyst has sort of come up with this scheme for what he thinks are the probabilities for this investment. So sorry, I didn't notice the words loss here, but it might be an $18,000 gain. It might be an $8,000 gain. There might be a 13, a 3, an 8, a loss of 2, a loss of 12, a loss of 22. So let's just say we don't know why he came up with these numbers and why, for example, there's not a $10,000. What's the probability that there's going to be a $10,000 gain? He didn't put that in here. He didn't say what's the probability there's going to be a $9,000 gain. So anyway, he just sort of divided it up into these different outcomes. It's not clear, at least from this slide, why they're like that, but you might do something like that. You might just make up some numbers, or they might sort of come from the analysis somehow, naturally come out of it. You might be analyzing some data and you say, oh, well, this might happen or that might happen. And then you have probabilities for each outcome that might happen. And so he thinks, and this is subjective, so it's not like you can't perform some experiment many times like we can with rolling a die 10,000 times. He just comes up with these numbers: 20%, 8%, 16%, 26%. It sounds kind of crazy to do this, but of course everybody does this, right? We all, assign probabilities to things, at least in our minds, at least unconsciously. So we can just think of it something like that. That's what's going on. So, so here's what we have, or here's what he has. Now, one thing though that's not just arbitrary. So you think, oh, these numbers are completely arbitrary, but they're not quite arbitrary. At least one thing we can say is, however he assigns these numbers, they better add up to 1. Otherwise, we can say, not only is it arbitrary, but it doesn't even make sense. So if these numbers don't add up to 100%, suppose they add up to, instead of 1, which means 100%, suppose they add up to 1.3, or in other words, 130%. When we say, oh, there's something wrong here, you can't, have all these probabilities add up to 130%. So at least we can say that has to be true. That we can't really, it seems pretty arbitrary the way that these numbers are being assigned, because we have no idea why he assigned them in this way. But it's not quite arbitrary. There is some logic or some rules that we can apply. And one rule is that they have to add up to 1. So, and here, apparently, it does add up to 1. Okay, so the next slide deals with what is meant by the word event. Now, on the blackboard just earlier, I gave a definition of what we mean by an event. That's not necessarily what every book uses. If a book is very mathematical, they'll do it the way I did. But a lot of books won't do that. And here, he's not quite saying it. So let's just recall what I said first. So taking a look at what we wrote on the board earlier, we had this sample space here. So we had this sample space here, and it was for tossing 2 coins. And we said HH, HT, TH, and TT. And then I talked about an event, which was blocked off here, which was getting exactly 1 head. And there are 2 ways that can happen. You can have a H and a T, or you can have a T and an H. Both of those give you exactly 1 head. So we call the event of getting exactly 1 head would consist of either this one or this one. In other words, we list the different ways within the sample space that it can happen. So I wrote it like this. And then I said, and I also said this was another event. This was the event of getting exactly 2 heads. And I somewhere on the screen I said, where was that? Somewhere on the screen, I don't remember, but I said that what do all the events that we talked about have in common? And what they have in common is that this is a subset of the sample space S, and this is another subset of the sample space S. So I said, hopefully I said somewhere, I don't see it on the board here, but hopefully I said this. An event is any subset of the sample space. So this is an event because it's a subset of the sample space. This is a different event because it is also a subset of the sample space. And we could construct other subsets of the sample space, and they would be other events. For example, and I think I said somewhere else. So I also gave this example, the event of getting a number greater than 3. That was when we were rolling a die. Rolling a die means we could get a 1, 2, 3, 4, 5, or 6 as the outcome. So that's the sample space. We could talk about the event of getting a number greater than 3. And we said that, or hopefully I did say that. So that was the event of getting a number greater than 3 is the subset 4, 5, and 6. So this is an event, getting a number greater than 3, and we can think of it as a subset of the sample space. Which subset? The subset which has the elements 4, 5, and 6. So I gave the definition that an event is just any subset of the sample space. An event is any subset of the sample space. Okay? Now that's not that necessarily every book does it that way. So here on this slide, that's not exactly what they say. They just say an event is a collection of sample points. But that's also what I said, because remember I said that the sample points were the elements of the sample space. So that's really what I just said when I said it was a subset of the sample space. It just means taking a collection of the sample points. So this is the same thing. They're just not saying it in terms of sets. So they're using the word collection instead of subset. The probability of an event is equal to the sum of the probabilities of the sample points in the event. So going back to the rolling a die, we have 1, 2, 3, 4, 5, and 6. And, the typical way is to say each one of them has a probability of 1/6. I'll put the sample space here, and I'll put the probabilities of the sample. Remember, these are called sample points. So I'll put the probabilities of the sample points above them, and they're all going to be 1/6. And then suppose I want to know what's the probability of getting an even number. So an even number is one of these numbers, 2, 4, and 6. So if I want to know the probability of getting an even number, the probability of that is equal to the probability of 2 plus the probability of 4 plus the probability of 6. That's 1/6 plus 1/6 plus 1/6, which is 3/6, which is exactly what we think is the probability of getting a even number. It's 1/6 because this is 1/6, and then this gives us another 1/6 because this is another way, and then this gives us another 1/6 because this is another way. So we add them up and we get 3/6, which is what we think. It's the probability of getting an even number is a half. So they say the probability of any event is equal to the sum of the probabilities of the sample points. So the event of getting an even number consists of this sample point and this sample point and this sample point. And then to get the probability of the three of them together, that is of getting an even number, we add up the probabilities of each of these. That's what this says. We can identify the sample points of an experimental and assign a probability to each. We can compute the probability of an event. If we can, sorry. Anyway, okay, so we want to decide whether that last example, whether this is going to be a good investment. So maybe this is from the book, and I don't understand what this is, and this is, and this is. So we'd have to read the book to get that. But anyway, what do we mean by that it's profitable? Well, we mean that it's one of the gains, not one of the losses. So one of the gains happens, not one of the losses. So what's the probability that it's profitable? Well, this, if it looks like this, it'll be profitable. If it looks like this, it'll be profitable. If it looks like this, this, or this. So that's the event that we're talking about when we say profitable. The sample space is the whole, all of these, or maybe that somehow, whatever this means, could also be called the sample space. But let's say this is the sample space. And then the subset called profitable or the event called profitable is this subset of this sample space, because these are all the gains. So if we want to know the probability of this event, the event of being profitable, what should we do? We should add up the probability of $18,000 gain, which is 20%, plus the probability of $8,000 gain, which is this, and we add these up. So we have to add up, I guess, these numbers here to figure out if it's what's the probability of it being profitable. The only way it's going to be not profitable is if one of these happen, and those are these probabilities. So that's what they do. The 20%, the 8%, the 16%, and the 26%. Those are these numbers here. 28, 16, 26, and 10. Is that right? They left out the 10. Why is that? They left out the 10, but they didn't leave it out of this number. Actually, when you sum up these numbers, you get 70%, I think. No, you get 80%. When you sum up these, you get 80%. So from that chart, it looks like this should have another plus 10%, and this answer should be 80. So I'm not sure what's going on.